Welcome to This Explainer. If you think urban planning is just about pouring concrete and laying down some pipes, well, think again. Today, we're exploring the real principles behind designing sustainable, waterwise human settlements, drawing right from South Africa's Neighbourhood Planning and Design Guide. We're looking at the living, breathing infrastructure that quite literally keeps our cities from running dry.
Here is our structural roadmap for today. First, the waterwise vision. Second, mimicking the natural cycle. Third, the development context. Fourth, the infrastructure toolkit. And finally, measuring demand and delivery.
All right, let's jump straight into Section 1, the waterwise vision, moving from policy to paradigm.
So, as we look at modern urban development, it really begs a massive question. How do we build neighborhoods that don't just, consume water, but actually protect it? We've reached a point where we can't just lay pipes anymore. We have to engineer living systems that safeguard our most precious, finite resource.
The answer to that question is a massive paradigm shift called water-sensitive urban design, or WSUD. It's exactly what it sounds like. Instead of fighting nature, we manage the urban water cycle by mimicking natural processes. The goal here is to treat every single drop as a scarce, valuable resource that gets integrated right into the city's blueprint from day one.
Because here is the core of the problem. In a natural environment, you get high infiltration. Water soaks into the earth and recharges the groundwater. But standard urban developments, they just pave over everything. We replace that natural absorption with hard, completely impermeable surfaces. And the result? Infiltration drops, and massive volumes of highly contaminated runoff flush straight into our rivers.
To fix this broken cycle, the regulatory framework gives us 4 universal pillars. Number 1, provide regenerative water services, meaning we only discharge what the environment can actually absorb. Number 2, create water-sensitive neighborhoods. Number 3, promote integrated management that links water directly to things like transport and housing. And number 4, empower water-wise communities. We are literally shifting from destructive habits to regenerative ecosystems.
Moving right along to Section 2, mimicking the natural cycle, turning theory into ecosystem.
A real game changer here is the use of sustainable drainage systems, or SUDs for short. It's all about flipping the script and treating stormwater as a resource, not a nuisance. Rather than just tossing runoff into massive concrete culverts, we can use permeable pavements, bioretention areas, and constructed wetlands. The water infiltrates the ground naturally, which, as an added bonus, drastically reduces downstream flooding.
Next up, Section 3, the development context, adapting to the environment.
Now, the solutions we actually use, they depend entirely on our canvas. If you're building on an untouched greenfield site, you must preserve those natural ecosystems. On a brownfield site, well, you're navigating around existing grids and heritage structures. And in informal, organically grown settlements, upgrading in situ means designing around totally unconventional layouts. The engineering strategy changes wildly depending on whether you're in a rural village or a dense urban core.
Which brings us to Section 4, the infrastructure toolkit, hardware for waterwise settlements. The actual physical journey of our water supply breaks down into 5 distinct stages. It starts way up at the macro level with the raw bulk supply, flows into water treatment, and then waits in storage. From there, it enters the reticulation network. That's the web of pipes beneath our feet, before finally reaching end-use delivery, right at the consumer's tap.
Let's zoom in on that storage stage for a second. Elevated metal water towers are absolutely critical. They don't just hold water, their physical height provides the vital gravity-fed pressure needed to balance out daily peak demands. And crucially, if the local power grid fails, gravity doesn't. That ensures emergency reserves keep flowing to the community no matter what.
But, towers aren't the only way to go. Depending on local geology and budget constraints, storage can be built directly on the ground. Prefabricated metal tanks are incredible when you need rapid deployment, while heavy-duty concrete reservoirs offer unmatched, long-term durability against the elements. When it comes time to lay the pipes, engineers face a classic trade-off. A branched network, where a main line splits into smaller and smaller submains, is highly cost-effective upfront, but a grid pattern with continuous loops offers incredible reliability. See, in a grid, water flows in multiple directions. If a pipe bursts, you can valve off just that one tiny section without leaving the entire neighborhood completely dry.
Finally, let's look at Section 5, measuring demand and delivery, the micro-level mathematics.
Before a single pipe goes into the ground, we have to figure out the demand. Otherwise, we risk drastically over- or undersizing the infrastructure. And the guidelines reveal a pretty fascinating truth about urban density here. Very high-density flats actually require significantly less water per unit, only around 0.25 to 0.3 kiloliters a day, compared to sprawling, low-density suburban stands, which can demand well over a full kiloliter.
Once the water is flowing, we absolutely have to track it, and picking a meter isn't just a one-size-fits-all scenario. We've got cost-effective mechanical multi-jet meters, we have highly accurate electromagnetic meters that have almost zero pressure loss, and ultrasonic meters that can easily handle poor water quality. And of course, there's the gold standard, smart metering, which allows two-way communication to catch unseen leaks in real time.
And finally, the water reaches the end user. While we often think of private yard connections, communal standpipes remain an absolute lifeline in many developments. These public taps guarantee a basic level of service, a minimum of 25 liters per person per day, ensuring that everyone has access to safe, potable water, entirely regardless of their economic status.
So why does all this meticulous planning even matter? Well, because the stakes are incredibly high right now. The source text ominously warns us that climate change is causing an increase in the frequency, intensity, and duration of extreme weather events. Severe droughts and massive floods can destroy infrastructure, contaminate drinking water, and just generally exacerbate global water scarcity.
So I want to leave you with a thought to really chew on. Is your local community's infrastructure built to just blindly consume water? Or is it resilient enough to actually protect your water-secure future? Are we engineering living, regenerative systems? Or are we still trapped in that outdated, destructive urban water cycle? Thank you for joining me on this explainer. Keep questioning, keep learning, and I'll catch you in the next one.